มนุษย์เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้าวิทยาลัยเพื่อการค้นคว้าระดับรากฐานสถาบันสำนักเรียนท่าโพประกาศจัดตั้งขึ้นเมื่อวันที่ 14 มีนาคม พุทธศักราช 2554 รับรองสถานะโดยสภามหาวิทยาลัยนเรศวรให้สถาบันสำนักเรียนท่าโพสำหรับฟิสิกส์ทฤษฎีและจักรวาลวิทยาหรือ TPTP ซึ่งแต่เดิมนั้นดำเนินการภายใต้จิตอาสาของเหล่าคณาจารย์ฟิสิกส์มาสเตอร์ทัพพาเอียนตั้งแต่แรกเริ่มเมื่อวันที่ 8 สิงหาคม พุทธศักราช 2539 ต่อเนื่องยาวนานจนเป็นสถาบันแห่งการผลิตผลงานศึกษาวิจัยและเป็นอาสมบ่มเพาะนิสิตสาขาวิชาฟิสิกส์ทฤษฎีให้มีความรู้ความเข้มแข็งทางวิชาการจนได้รับการยกสถานะให้เป็นหน่วยงานระดับคณะวิชาอย่างเป็นทางการถือเป็นการประกาศเจตนารมณ์ผลักดันยุทธศาสตร์พิเศษของมหาวิทยาลัยนเรศวรที่จะก้าวเป็นมหาวิทยาลัยวิจัยชั้นนำของประเทศในระยะเวลา 10 ปีที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตผลงานต่างๆมากมายผลงานวิจัยตีพิมพ์ระดับนานาชาติจำนวน 125 บทความผลงานวิจัยตีพิมพ์ระดับชาติจำนวน 8 บทความงานประชุมวิชาการระดับนานาชาติจำนวน 7 ครั้งงานประชุมวิชาการระดับชาติจำนวน 10 ครั้งการจัดอบรมเชิงวิชาการระยะสั้นและโครงการบริการวิชาการจำนวน 58 โครงการการจัดสัมมนาวิชาการ 200 ครั้งคณาจารย์ของวิทยาลัยได้รับรางวัลเชิดชูเกียรติทางวิชาการจำนวน 15 รางวัลบันทึกข้อตกลงความร่วมมือกับสถาบันชั้นนำอื่นๆจำนวน 13 สถาบันหนังสือและตำราวิชาการจำนวน 13 เล่มวิดีโอสอนออนไลน์ผ่าน IF Channel จำนวน 34 วิดีโอนอกจากนี้ SIP Plus Consortium ได้สร้างเครือข่ายความร่วมมือทางวิชาการระหว่างสถาบันฟิสิกส์กว่า 20 สถาบันกลุ่มเครือข่ายพิษณุโลกฟิสิกส์เน็ตเวิร์กได้ส่งเสริมกิจกรรมสัมมนาวิชาการในจังหวัดพิษณุโลกและสถานีฟิสิกส์ศึกษาคือการให้ความสำคัญกับครูผู้สอนฟิสิกส์ในโรงเรียนระดับมัธยมศึกษาให้เข้มแข็งและถ่ายทอดสู่นักเรียนผู้เป็นอนาคตของประเทศที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตบัณฑิตสำเร็จการศึกษาในหลักสูตรวิทยาศาสตร์มหาบัณฑิตจำนวน 8 คนหลักสูตรประกาศนียบัตรบัณฑิตชั้นสูงจำนวน 10 คนหลักสูตรปรัชญาดุษฎีบัณฑิตจำนวน 5 คนผลงานเหล่านี้จะสำเร็จขึ้นมาไม่ได้หากปราศจากผู้สนับสนุนและแหล่งทุนวิจัยอาทิมหาวิทยาลัยนเรศวรสำนักงานกองทุนสนับสนุนการวิจัยสกว.สำนักงานการวิจัยแห่งชาติวช.โค ครงการปริญญาเอกกาญจนาภิเษก คปก.นิวตันฟันด์ศูนย์ความเป็นเลิศด้านฟิสิกส์เทพสถาบันวิจัยดาราศาสตร์แห่งชาติองค์การมหาชนมูลนิธิโทเรเพื่อการส่งเสริมวิทยาศาสตร์ The Abdus Salam International Center for Theoretical Physics ICTP อื่นๆปัจจุบันวิทยาลัยเพื่อการค้นคว้าระดับรากฐานมีคณาจารย์ทั้งหมด 9 ท่านโดยแบ่งเป็นคณะผู้บริหารวิทยาลัย 4 ท่าน 3 ห้องปฏิบัติการวิจัยห้องปฏิบัติการวิจัยจักรวาลวิทยาและความโน้มถ่วงห้องปฏิบัติการวิจัยทฤษฎีสนามควอนตัมและฟิสิกส์พลังงานสูงหน่วยวิจัยฟิสิกส์ดาราศาสตร์และจักรวาลวิทยาเชิงคำนวณจากอดีตถึงปัจจุบันเรายังคงดำเนินการภายใต้พันธกิจสำคัญอย่างต่อเนื่องดังประกาศเจตนารมณ์ท่าโพณวันที่ 8 สิงหาคม พุทธศักราช 2539 เราจะสร้างโรงเรียนฟิสิกส์ที่ดีที่สุดแห่งหนึ่งของประเทศขึ้นที่นี่โดยหวังเป็นอย่างยิ่งที่จะส่งเสริมสังคมแห่งการเรียนรู้จุดประกายเยาวชนและสร้างบุคลากรให้มีความเข้าใจลึกซึ้งเห็นถึงความสำคัญของวิทยาศาสตร์พื้นฐานต่อยอดวิทยาการความรู้ด้านต่างๆให้ก้าวหน้าบนรากฐานที่มั่นคงทางวิทยาศาสตร์ซึ่งเป็นกลไกสำคัญให้ประเทศไทยขับเคลื่อนไปอยู่ในระดับแนวหน้าของโลกในอนาคต
Good afternoon, everyone. Welcome to IF Colloquium Online Seminar Series No.1, organized by the Institute for Fundamental Study, No.1 University, Thailand. My name is Seklin Yukong. I am IF Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon online event. Let me first give you the idea behind this event. Most of the time, academic conversation would normally circulate among the scientists, yet it's bridging the gap between the science world and the general audiences is very crucial for the country in this current competitive world. Then the Institute for Fundamental Study would like to provide a platform for the people who are interested in physics, mathematics, and other related fields come and enjoy in progress of the advanced research. For this talk No.1, we are very pleased to have Associate Professor Dr. Thilapong Pongmari from Khon University to give us insight about fighting cancer with computational nanophysics. Let me spend a little bit more time to introduce our speaker formally. Dr. Thilapong Pongmari received his bachelor degree in physics, first class honor with a gold medal from Khon University. Then he pursued his master's degree in nanotechnology with distinction and a PhD in quantum electronics from School of Electronics and Electrical Engineering, University of Leeds, United Kingdom. At the moment, he is working as an associate professor at Department of Physics, Faculty of Science, Khon University, Thailand. His research interests, correct me if I'm wrong, on the interface between computational physics and medical science. The talk would be roughly 40 minutes long. Before I stop doing the talk, if you have questions, you can send us in the chat box. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give this screen to our speaker, Dr. Thirupong Pongmali.
Okay, right. Thank you, Assistant Professor Sikarin Yukong from the Institute of Fundamental Study. And I would like to thank the Institute for your kind invitation from me to have a good opportunity to give a talk to all the broad audience about my research. So let me introduce myself. I am a lecturer from Material Science and Nanotechnology program, as earlier mentioned, and I am from Department of Physics, Faculty of Science, Konkan University. And the title of my talk today is related to the cancer, and what we have done so far in our research group is to use computational nanophysics to design nanomaterial in order to detect some biomolecule, which is the indicator of cancer, of several cancer, which is called biomarker. So before we go to what I have done so far, let me introduce everyone about the occurrence of cancer around the world. The cancer that have been found so far around the world is more and more increased. And recently it was reported in 2019 that most of the cancer patterns are from Asia. And if we look at the people from Asia, we found that several cancers have been observed and have been reported recently. So it's quite a good idea to develop and use some nanomaterial in order to detect or to tell everyone that you are likely to be cancer in the early stage and in the early time. So in our research, we try to find what can tell us about the early stage of the cancer. And if we look at the many biomarkers, we found that what is called DNA methylation is something that is closely related to the risk of the cancer. So before we go to my research, let me briefly explain everyone about DNA methylation. If you look at this slide, you can see what you are quite familiar, which is called the cell. And if you look inside the cell, you can see the nucleus. And inside the nucleus, you can see what is called chromosome. And if you stretch the chromosome, you can see a strand of the DNA. And if you look at the strand of DNA, you can see that it is double strand. So each strand of the DNA is called single strand DNA. And if we closely look at each unit of the DNA, we found that each DNA is composed of nitrogenous base, or A, T, C, G, or adenine, thymine, cytosine, or guanine. And also the deoxyribose, which is a sugar, deoxyribose sugar, and also the phosphate. This is the unit of the DNA. And then if we look at the relationship between the DNA and the cancer, specific genetic information of the DNA is related to the cancer. And if we look at the single-strand DNA, and it was found that in some region, which is called CPG size, this size is closely related to the cancer. What is the CPG size? The CPG size is the position in the single-strand DNA, which can be found cytosine close to guanine. So if you stretch the single-strand DNA of the cancer cell, you will find the CPG site quite a lot in the single-strand DNA of the cancer DNA. So the next step is to think about how can we detect the DNA methylation in the DNA. So if we look at the cancer cell of the, if we look at the DNA of the cancer cell, we found that for the single-strand DNA in some specific region, which is cytosine, there is a biological process which is called DNA methylation. The DNA methylation is a biological process with the methyl group, which is CH3, is added to the 5th position of the carbon atom in the cytosine. And if we look at the different cancer type, for example, cancer A, B, and C, it was found that the methylcytosine is frequently found in some region, which is called CPG size. And if you compare the difference between A, B, and C, which is cancer A, cancer B, and cancer C, the similarity is the cluster of the CPG size. So the cluster of CPG size has been found for every cancer. For example, cancer A, B, and C, as shown in this figure. And the next step is we have to think, what is the similarity between each cancer? It was recently reported by this group that the DNA methylation affect the physical chemical property of the DNA in the solution. If we look at this figure, the upper figure is the normal DNA and the lower figure is the cancer DNA. So the difference between these DNA is the conformation of the DNA in the solution. Is due to the hydrophobic property of the methyl group that are added into the single-strand DNA. Methyl group is very hydrophobic. So in short, it doesn't like water. So if you have the cancer DNA, there's a cluster of methylcytosine in some region. But in contrast, for the normal DNA, the DNA methylation can occur along the single strand of the normal DNA. So the hydrophobic property between these two types of DNA are different. And then if you put the DNA into the solution, you can see something different. For the normal DNA, the aggregation can be obviously found. In contrast, for the cancer DNA, the aggregation is not found for the cancer DNA. So I show you in this figure that for the normal DNA, the rigid aggregation of the DNA can be obviously observed. In contrast, the cancer DNA, it can distribute in the water. So this is one of the common property of several cancer DNA. So we will use this property to be a universal cancer biomarker. And if you have the DNA from your blood, what you can observe is to see how it distributes in the solution. If your DNA is look like this, it implies that your DNA sample is normal. But if the conformation is different like this, it can be told that the DNA is cancer. So in order to detect the difference between normal and cancer DNA, many researchers have proposed many techniques. And one of the most easy techniques is to use the metal surface. If you have the normal DNA and the cancer DNA, and you put it into the solution, and then the difference between normal DNA and cancer DNA is the absorption of this DNA on the surface of metal. In the case of the normal DNA, it forms rigid aggregation. So there's a small area that it can absorb onto the surface of the metal. In contrast, the cancer DNA distributes throughout the solution. So it can absorb on the metal surface very nice. So we will use this basic property to differentiate normal and cancer DNA. And how about the material that we can use to detect the difference? The material that in our research group used to detect the difference between normal DNA and cancer DNA is shown in this figure. We are interested in the gold nanoparticle and the quantum dot. They have very unique property and have size-dependent property, and the distribution of this nanoparticle in the solution affect their property also. So we are interested in two types of nanomaterial. Apart from gold nanoparticle and quantum dot, in this case we use carbon quantum dot, we also interested in graphene oxides. And what is the graphene oxide? The graphene oxide can be easily understood from the figure shown here. The graphene structure is composed of the benzene ring of carbon atom, and the concrete example of the graphene is the pencil. But in the case of graphene oxide, it is functionalized with some functional group. As shown here, the functional group that functionalized on the graphene oxides, the graphene surface are carboxyl group, which is COOH, and hydroxyl group, or OH, and epoxy group. These are the basic functional group that functionalize on the graphene oxides. And the reason that why we are interested in the graphene oxide, the graphene and graphene oxide have different property. In the case of graphene oxides, in terms of physics, it was found that there's the band gap of the graphene oxides. So it means that the band gap can be changed or can be tuned by the number of functional groups on the surface of the graphene oxides. So another property of the graphene oxide that are very interesting is the graphene oxide the electrical property of the graphene oxide can be easily tuned if you have the biomolecule on the surface of the graphene oxide. And in addition, the graphene oxide is also biocompatible material. So it can be applied in the biomedical application. So in this case, in our work, we use the graphene oxides to detect and differentiate two different things. The first one is normal DNA, and another one is the cancer DNA. So how can we use the graphene oxide to differentiate the difference of normal DNA and cancer DNA? This is the working principle of the graphene oxide-based field effect transistor. Just imagine that you have a small circuit chip, and for the circuit chip, you have the electrode, which is called source and drain. And this chip is connected by graphene oxide in between this electrode. And in order to detect and differentiate the normal DNA and cancer DNA, we need to measure the electrical conductivity of the graphene oxide when the DNA is on top of the graphene oxide. So in order to investigate and design the field effect transistor, or FET, we use the computer simulation to design and to gain insights into the molecular interaction between the cancer DNA and the graphene oxides. And in our study, we used a P53 gene of skin cancer, which is just a small piece of DNA that can be found in skin tumor. So a small piece of P53 gene has a sequence as shown here. As you can see that cytosine and is close to guanine, many positions. So these are called CPG sites. And I will call this single-strand DNA as unmethylated DNA. But in the case of cancer DNA, as I explained in the first few slides, that there is a biological process which is called DNA methylation. So the cytosine is converted to 5-MC, which is called 5-methylcytosine. So this is the example. This is the sample strand of normal DNA and cancer DNA. So next, we will use computer simulation based on the knowledge about nanophysics to investigate and to gain insights into the molecular interaction between these two DNA and the graphene oxides. And in order to observe what happened in the molecular level, we have to use what is called computational microscopy. Computational microscopy is like the technique that you can use to observe what happened in the molecular level. You can see the interaction between atoms. It can attract or it can repel to each other. And in the world of computational study, there are many tools that we can use to investigate this interaction. For the small molecule, we use the density functional theory, or what is called DFT. DFT calculation can be used to investigate the electronic structure of some biomolecule or some small system. But if you are interested in the larger size or larger system, for example, in our case, we have to investigate the interaction between the DNA and the graphene oxide. We have to move to another tool, which is called molecular dynamic simulation. Molecular dynamic simulation is based on the Newton's second law. And in this simulation, the basic principle of the molecular dynamic simulation can be explained briefly here. Firstly, we have to know the interaction between each atom. If the atom have bound together, it have the term here, which is the potential between atom that is chemically bound together. If the atom quite far away from each other, there are some interaction, for example, electrostatic interaction or Lennard-Jones potential that can be used to explain the interaction between the atom that is quite far away from each other. So in short, you have to sum all the interaction that happen in the molecular level, and we call here as V total. And then if you understand clearly about the V total or the system, you can calculate the force acting on each atom. And then based on the Newton's second law, you can calculate the interaction and the force acting on each atom, and you can observe the movement of each atom. This is the basic principle of the molecular dynamic simulation. And to get something about the potential that I just previously explained in the previous slide, the potential that we have to take into consideration are as follows. If you have 4 atoms in your system, you have to think about the interaction between atoms. If 2 atoms have bound together, this term can be used to explain. And if the atom have the angle, for example, this atom, this and this term can be used to explain. And we use the similar method for the consideration of other atoms. These are the terms that can be used to explain the first term in the previous slide. For the non-bond potential that can be considered in the simulation are classified into Lennard-Jones potential and also electrostatic interaction in the case that the atom have the charge. So these are the basic principles of the molecular dynamic simulation. And after that, as I explained before, we have to solve the Newton's second law in order to observe the trajectory of each atom in your system. So in our work, we use this tool to investigate the interaction between normal DNA and cancer DNA and the graphene oxides. And in order to make it clear about the next slide, I will explain about the result from our recent work. Let me briefly separate our work into 5 sections. The first thing that we will try to observe is the interaction or the conformation of the single strand DNA when it absorbs on the graphene oxide. And next, we try to have a look what's happened when it absorbs on the graphene oxide. So these are based on molecular dynamic simulation. And in order to gain some information about the absorption of the DNA on the graphene oxide, we have to use density functional theory to calculate some absorption energy, which can be used to explain what's happened in the molecular level. And next, in the reality, in the blood sample, double-strand DNA can be frequently found in your blood. So we try to move from single-strand DNA to double-strand DNA. And then the last part is the observe of the role of cation in the absorption of DNA on graphene oxides. Because normally magnesium chloride is added into the solution in order to increase the stability of the biomolecule. So the role of magnesium ion on the DNA absorption will be explained in the last part. So these are the overview of our research that I will explain in the next slide. So let's start with the first part. What's happened when DNA absorbs on the graphene oxides? And based on the molecular dynamic simulation or MD simulation, just imagine that you have a small box, and then in the box at the bottom you have graphene oxides, and you put some water molecule into the box, and we call this box as simulation box. And then you put the DNA into the simulation box, and you observe what's happened in 200 nanoseconds. So in order to easily understand about the next slide, I will use the color code for each system. So the blue one is in the next slide, or from this slide, I will divide our simulation result into 4 different systems. The first part is the DNA in the water, which are represented by the blue and the green one. The blue one represents the result from unmethylated single-strand DNA. And the green one is the result from methylated single-strand DNA. So just imagine this is the results for normal DNA, and this is the results for cancer DNA. And in addition to the interaction in the water, we also observe in the magnesium chloride solution. So the basic thing that we observe is to see what's happened when you have normal DNA and cancer DNA on the surface of graphene oxide. And this graph shows our simulation result. And let me briefly explain about the graph. The x-axis is the simulation time, starting from 0 nanosecond until 200 nanosecond. So in order to see the interaction between DNA and the graphene oxide, it has to be conducted for 200 nanosecond. And the y-axis represents the contacting surface area, or in short, CSA, or contacting surface area. What is the contacting surface area? The contacting surface area is the area of the DNA that it absorbs on the graphene oxide. So we use computer simulation to observe from the beginning until the end of the simulation. From our simulation, we found something that is quite interesting. If you look at this graph, if you have the higher value of CSA, it means that DNA can absorb to the graphene oxide easily. So if you look at this graph, you can see that the green one and the blue one is totally different. And if you look at the caption here, the blue and the green one are unmethylated single-strand DNA and methylated single-strand DNA in water. So it means that if you have the normal and cancer DNA in the water, the absorption of the normal and cancer DNA are different. In the case of magnesium chloride solution, or the orange and the red line, we found that the contacting surface area are similar or quite close to each other. So this result suggests us that in order to differentiate normal and cancer DNA, you have to perform in the water, and you can have the different contacting surface area of the DNA on the graphene oxide. So this is the first result that we found, and it's quite interesting. So we will use another tool to analyze what's happened when the DNA absorbed on the graphene oxide. And we use the basic physics to calculate the curvature of the DNA during the absorption on the graphene oxide. And what I show here is the complicated graph. And let me briefly explain what it means. The graph shows the curvature of the DNA during absorption, and it is coded by the color. If you see the white color, it means that there is no curvature, so the DNA is quite straight. If you see the blue color, it means that the DNA is quite curved. So we observe from the beginning, which is the t equal to 0, until the end of the simulation, which is 200 nanoseconds. And the y-axis represent the nucleobase, start from cytosine, guanine, until guanine. So if we look at this graph, there's something quite interesting. We see that the blue area in this case quite obviously observed. We see here, here, and here. So it means that the methylated single-strand DNA in the water absorbed on the graphene, and it shows 3 curvature of the DNA during absorption. And the snapshot at this figure, which is the snapshot at the end of the simulation, clearly show that the DNA completely absorbed on the graphene oxide. So this also confirms that in the water, the DNA fully absorbed on graphene oxide. Methylated single-strand DNA fully absorbed on the graphene oxide. In contrast, in the water also, unmethylated single-strand DNA can partially absorb on graphene oxide. But in the case of magnesium chloride solution, we cannot see any difference in terms of contacting surface area or in terms of absorption, because if you look at this snapshot, it's quite similar. So in the next slide, we will try to analyze what's happened. Why in the water we can see the difference of the absorption of the normal and the cancer DNA. We use another tool, which is the analysis of the angle of the DNA during the absorption. And again, if we analyze 4 different systems, which are the DNA in the water and magnesium chloride, and the DNA in water and magnesium chloride, and they are divided into 4 different systems. We see something in this analysis. We use the vector analysis to calculate the angle of the DNA, of the normal DNA and the cancer DNA during their absorption on graphene oxide. What we see is for the blue and the green one, they show different angle. For the blue one and green one here, as you can see here, the blue one is unmethylated single-strand DNA in the water. And the green one is the methylated single-strand DNA in water. And again, the angle of the curvature of DNA in the water can be clearly observed and can be easily differentiated between unmethylated and methylated DNA in water. So taking all the results from the beginning until now, we suggest that in order to see the difference between normal and cancer DNA, the experiment have to be conducted in the water. And next, in order to understand what's happened, why methylated DNA can be easily adsorbed on the graphene oxide, we use the density functional theory based on vast package to calculate the adsorption energy between the nucleobase and the graphene oxide. In this slide, I showed interaction between the nucleobase, which are cytosine and 5-methylcytosine. And in this calculation, we cannot completely see what's happened in the whole DNA. It's because in order to gain insights into the DFT world, you have to shrink the system to be a smaller system. So in this system, we have the graphene oxide here, and it is functionalized with some functional group. And in this figure, it is functionalized with epoxy group here. And on top of this epoxy group, we place two molecules. This molecule is cytosine, as shown here. And for the lower one, we place the 5-methylcytosine. So in this calculation, we try to find some explanation why methylated DNA can be easily adsorbed on the graphene oxide. And from the DFT calculation, it was clearly shown that there's something happened in the absorption of 5-methylcytosine. As shown here, the blue and the yellow area represent the density of the electron, which in the case of yellow, it shows the high electron density, and the blue one shows the low electron density. So if we look at the lower one, you can see that 5-methylcytosine have the methyl group here, which is CH3 here. And you can find that the high electron density are around here. So based on the DFT calculation, we conclude that during the absorption of 5-methylcytosine, there is electron transfer, the transfer electron from this methyl group to the graphene oxide. And it also affects the absorption energy of these two molecules. And we found that the absorption energy of the cytosine is about minus 0.34 electron volt. In the case of 5-methylcytosine, the absorption energy is about minus 0.45 electron volt. So this implies that the methylcytosine has the higher absorption energy. Briefly, it can easily absorb on the graphene oxide, which is functionalized with the epoxy group. And if we look at the density of state of this system, we found that the electron is transferred into graphene oxide plate. And then we can find some state in the valence band. So briefly, when the cytosine are on the graphene oxide, there's electron transfer from methyl group to the graphene oxide, and it shows high absorption energy. This is the reason why the methylated DNA can be easily absorbed on the graphene oxide. And next, we try to calculate the similar things to the previous slide, but we observe in a different size. We observe the absorption of cytosine on three different things. The first one is the absorption on cytosine on bare graphene. And the next one is the absorption of cytosine on hydroxyl group, graphene oxide with functional with this group. And the next one is the absorption of cytosine on graphene oxide with which is functionalized with this functional group. So from this result, we compare the difference between the absorption energy between cytosine and 5-methylcytosine. We found that if you look at the graphene sheet, the absorption energy between cytosine and 5-methylcytosine are quite high. So it means that the cytosine and 5-methylcytosine can be easily absorbed on the graphene. So graphene solely cannot be used to observe the difference of the absorption between these two molecules. And during the absorption, it also affects the band gap of the system. In terms of cytosine on the graphene, the energy gap is equal to 1.2 millielectron volt. And in the case of 5-methylcytosine, the band gap is slightly different, which is 1.6 millielectron volt. So this suggests that graphene cannot be used to differentiate between cytosine and 5-methylcytosine. And in the case of graphene oxides, and we observe the absorption of these two molecules again on two functional groups, which is hydroxyl group and epoxy group. We found that in the case of this group, the absorption energy is quite different, resulting on different band gap of the system. In the term of cytosine, the band gap is about 9.5, but in contrast, in the case of the absorption of 5-methylcytosine, the band gap is about 12.9 millielectron volt. So this is the beginning of our study that we found that this can be applied as the detection of cytosine and 5-methylcytosine. And as I mentioned in the first few slides, in reality, if you would like to design some chip in order to differentiate normal DNA and cancer DNA, in reality, the DNA is the DNA in your blood that you can mostly found in your blood are double-strand DNA, and then we have to observe the interaction between the double-strand DNA and the graphene oxide. And in our simulation, we perform the same thing as the single-strand DNA. We have the simulation box and the graphene oxide and the water, and we put the double-strand DNA into the simulation box and observe what's happened during the absorption. What we found is quite interesting. In the case of double-strand DNA, it was found that the absorption of all cases are quite similar. If you look at this graph, the x-axis represents the simulation time, starting from when you put the DNA into the simulation box until the end of the simulation. And the y-axis shows the contacting surface area. After we performed the simulation for 200 nanoseconds, it was found that every case, the DNA can be absorbed onto the graphene oxide with a similar pattern. So graphene oxide cannot be used to differentiate normal double-strand DNA and cancer double-strand DNA. So in order to observe what's happened when the double-strand DNA absorbed on the graphene oxides, we try to zoom into the interaction region. We found that at the end of the double-strand DNA, there is a nucleobase and this nucleobase can absorb on the graphene oxide easily. So this is the reason why the 4 different cases of the simulation system show similar pattern during the absorption. However, we found something that different and can be used to differentiate normal DNA and cancer DNA. We analyze the angle of the DNA during absorption. Just imagine that if you have the DNA and you have graphene, and we try to look at the angle between the double-strand DNA and the graphene sheet. After we perform the simulation for 200 nanoseconds, there's something different. We can see the difference of the angle of the DNA during absorption. The x-axis shows the simulation time starting from 0 until 200 nanoseconds, and the y-axis represents the angle between DNA and graphene and how can it absorb on the graphene surface. What we see is in the case of green and red line, which is methylated double-strand DNA in water and in magnesium chloride, the angle is higher than 45 degree. In contrast, for the purple and the blue line, which are unmethylated double-strand DNA in water and in magnesium chloride, respectively, the angle between the DNA and the graphene oxide is less than 45 degree. So this is the signature difference between normal and cancer DNA during absorption. And the question is, what's happened? Why the methylated DNA can stay like this when they absorb on the surface of the graphene oxide? What we can explain is the addition of methyl group to the cytosine will increase the rigidity of the DNA, and then it also increased the conformation of the DNA during absorption. So that's why methylated DNA can have the angle more than 45 degree once it absorbs on the graphene oxide. So let me summarize some difference between normal and cancer DNA. The normal DNA will are likely to stay in the plane along the graphene nanosheet. In contrast, the cancer DNA will stay like this during absorption. However, we cannot use this signature difference to differentiate by our sensor chip. And the last question is, if we have the ion in the solution, how the ion affect the conformation or the absorption on the graphene oxide? It was found that magnesium ion in the solution can affect and result in 2 issues. The first issue is the graphene oxide are negatively charged, and the magnesium ion are positively charged. So the magnesium ion will stay on the surface of the graphene oxide due to the electrostatic interaction. And this can reduce the electrostatic interaction between the DNA and the graphene oxides. This is the first issue that is a result of magnesium ion concentration in the solution. In addition, the addition of magnesium ion in the solution can result in the bridging between DNA and the graphene oxide. As we know that the DNA are negatively charged and the graphene oxide are also negatively charged. And the magnesium ion is the bridging between these 2 systems to come closer. So that can be used to explain why in the system of magnesium ion, you cannot see the difference between the absorption of normal DNA and the cancer DNA. So let me summarize what I explained so far in my talk today. Based on our study, we used the molecular dynamics simulation to investigate what's happened in the molecular level. And based on our molecular dynamic results, we suggest that DNA methylation detection should be conducted in water. So if you have a drop of water on the graphene oxide, the absorption between normal and cancer DNA will be different. And the difference of the absorption can result in the different electrical conductivity of the graphene oxide. So you can measure the electrical conductivity of the graphene oxide and then try to two different things from the electrical conductivity. And based on the DFT calculation, our simulation suggests that the hydroxyl group can be utilized to determine cytosine methylation. As I explained about the band gap, when you have the cytosine or methylcytosine on the hydroxyl group, the band gap of these two systems are quite different. So if the band gap of the graphene oxide, which are attached to methylcytosine, are different, this results in different electrical conductivity also. So based on our simulation, we we think that, and we deeply believe that our finding can pave the way or open the door for the novel designs of the graphene oxide-based biosensor, and we can use this to differentiate the DNA that can be extracted from the blood, and then you can use this sensor chip to differentiate the difference of the DNA in terms of different electrical conductivity. And the work that I explained so far has been recently published in the Journal of Physical Chemistry B, and our work was selected by the editor to show up as the cover of the journal, and it's shown here. And this is something that we are quite proud of our work, and it's something that drives our energy to work more. And in addition to the biosensor, we also use molecular dynamics simulation to design other biosensor. For example, we use the molecular dynamics simulation to observe the interaction between gold nanoparticle and biomarker here, which is called 8-oxo-DG. This is the biomolecule that can be found in the urine. And if you have high concentration of the 8-oxo-DG molecule in the urine, it can be a good indicator of the risk of many cancer. And we use the gold nanoparticle and the computational simulation to design gold nanoparticle to capture this molecule, and it can be shown by the color, and we can observe by the naked eye. And these work are published last year, and they are also selected as the journal cover, as shown here in the Journal of Physical Chemistry B, and also the ACS Omega. And apart from this, we also use the computer simulation to investigate what's happened in the border between in the interface between gold nanoparticle and the membrane of the cell. And we use the molecular dynamics simulation to investigate what's happened and what parameter that can affect the cellular uptake of this nanoparticle. And we found that different size, different shape, and different surface functionalization can affect the cellular the cellular uptake of this nanoparticle. So if we understand the mechanism of the nanoparticle into the cell, we can use this to design uh, the nanoparticle for the drug delivery. And again, our work were selected as the journal cover and in the Journal of Physical Chemistry C and B last year. And all of this work have been done in my research group. And last but not least, lastly, I would like to thank I would like to give a big thank to all of my teamwork and my co-worker. These are my students in our research group. Our research group is Smart Nanoparticle for Nanomedicine. We try to design nanoparticle to be a smart particle in order to be applied in biomedical application and so on, and so many various applications. And in our research group, there are five PhD students and three master degree students, and also one research assistant and here. And in our research group, we carry out both experiment and computer simulation. And these skills are based on experimental study, and these guys are based on computer simulation study. And last but not least, in order to complete one research, collaboration is very important, and I think it's just like the key of the research. We have a great collaboration with many researchers. For example, we have a collaboration with chemists and material scientists. Associate Professor Piwat Chompusaw, who is now currently working in Department of Chemistry at Ramkhamhaeng University. Many years ago, he used to work in Konkan University, and then he moved to Ramkhamhaeng University for some reason. And we also work with biochemists. I would like to give a big thanks to Ajahn Chadama, Assistant Professor Chadama Sukunsin Siri, and Assistant Professor Renu Thanan, who are key person about the basic biochemistry. Sometimes I'm a physicist, so I need to consult with biochemists to understand something that we have never learned before. And last but not least, we try to move to a step forward, and we try to push our work into the practical realization. So I work with Ajahn Thanapong and Ajahn Dalaswin from Rashapat Buriram University from Buriram, and Ajahn Thanapong from Department of Statistics in Konkan University, who are working on data analysis, and we try to move to a mobile phone biosensor. And lastly, I would like to thank Institute of Fundamental Study for your kind invitation for giving a talk today, and I hope you enjoy with my talk. Thank you very much. Thank you.
All right. Thank you very much. Very interesting and wonderful talk, I think. Well, when I see some picture of your in your talk, something like curling up here, like a DNA strand,
Yeah.
I could think about, well, math in terms of the topology. I don't know, is that something to do with topology in order to study this kind of DNA thing? I don't know.
It might be. It might be. Yeah, that's quite a good idea to have something in topology in the DNA. But we might have to discuss some aspect that we can apply topology in terms of DNA or in terms of the biosensor or something like this.
All right. Okay. But I think the interesting point is that the physics that you used here is very simple. But that is not the bad thing, because this kind of simple physics could make like a very huge impact right here. Well, as you mentioned about, well, how you could create the way that you can detect the cancer, right? This by use this kind of technique. I think it's very interesting, like area of research, right? Yeah. But you need a lot of, well, background, I believe, not only physics, you need also chemistry, biology, and also coding, I believe, right?
Yes. For some people who are interested in the biophysics world, and like I have done so far, honestly, at 10 years ago, when I studied in the University of Leeds, I studied something that is totally different from I present today. But when I come back to Thailand, and I think what we can work with my friend from department or from faculty of medicine, from other faculty, and I found that molecular dynamic simulation is a very powerful tool that we can apply to design something that can be applied in the practical application. And in the next 2 months, we will publish two interesting work which are based on very easy method that can use to design gold nanoparticle instead of using graphene oxide, and used to detect normal cancer DNA based on molecular dynamic simulation. And interestingly, we have some experimental result, and it goes together quite well. And next, we think that if this work well with the cancer screening, it can be used to screen the cancer pattern in about half an hour, nearly half an hour.
All right. Okay. Well, when you mentioned about your PhD time, well, that's remind me about, well, we actually met there when actually we did PhD at the same university, right? University of Leeds, and I could recall. Well, I think if I remember correctly, what you did in your PhD is something to do with the quantum dot, right?
Yeah.
Okay, yeah, that is very interesting for the young people here, because it's not necessary to continue. Well, I mean, what it means is that, well, what you did when you are in your PhD is one thing. And after you finish, you might kind of stress away a little bit to something else, right? That you are interested in, right? This is very good example.
What I would like to suggest PhD student or other student that are listening to this talk, PhD life or master degree life is something that you can learn some skill that can be applied in your future. If you can continue what you study in your PhD study in the next level of your career path, it's a good things and a good way that you can continue your work. But you don't need to stay in the same position. You can move to another position, and based on the skill that you have learned in your PhD life, and apply what you have learned so far in another or different field of study. And in my case, what I study at the moment is totally different from what I study in my PhD study.
Yeah, very good. I think, yeah, very good. Well, there is a question from the online. The question is that which technique was used to prepare the sample, PRC, LAMP, or anything else?
You mean the extract of the DNA?
I don't know, because maybe the DNA, I believe.
Okay. In the detail of the extraction of the DNA, we have researcher from biochemists, as I show in the last slide. And basically, you extract the DNA from the blood. In terms of experimental study, you extract the DNA from the blood, and then we have some solution. It's like the protocol that is basic protocol to extract the DNA from the blood, and then you can use something to transform from double-strand DNA to single-strand DNA. As I explained in my talk, that we do not suggest to use our idea to apply for the detection of double-strand DNA. So one thing that the experimentalists have to do is to split the double-strand DNA into the single-strand DNA and then apply it onto the circuit.
All right. So what about how to prepare the graphene that you use?
In terms of graphene oxide, we are still looking for the collaboration from you guys here. So today,
not for me, definitely.
Today, I think is a good opportunity for me to give a talk online. You know, at the beginning, I'm so excited to give a talk online. After a few moments, oh, okay, that's fine. And if you guys are listening to my talk and you are working on graphene oxides and you think that we can apply this idea into the practical application, please contact us, and we are happy to change some idea to you guys and to develop the chip. So in short, we complete only computer simulation, but in terms of graphene oxide-based biosensor, we're still looking for collaboration for the experiment.
All right. Okay. There are more questions actually. The first one is it possible to reduce simulation time in dsDNA absorption? Because I see different in CSA in 50 nanoseconds.
Okay. Okay, that is a good question. Can you share the screen into
Yeah, I think.
Okay. As I show here, there's different level of computer simulation. If you look at a small system, density functional theory is very suitable to observe, and you can get so many things from DFT calculation. But in our study, we use molecular dynamic simulation, which is based on all atom simulation. So we have all atoms in the system are taken into consideration. So in this study, if you like to observe for 200 nanoseconds, it has to be conducted quite a long simulation time. Another way to get this simulation shorter is to use coarse-grained simulation. Coarse-grained simulation is some simulation that show here. It's the simulation that you reduce the number of particles in your system. If you have some molecule that have similar property, I mean chemical property, you can group it to be 1B. And then from the whole system, which is about 1 million, roughly speaking, 1 million atom, it can reduce to nearly 500,000. And then it can reduce the time of reduce the simulation time. And in addition, if the question is it possible to perform the simulation less than 200 nanoseconds? The reason that we perform the simulation for 200 nanoseconds is we would like to make sure that there's some difference between normal and cancer DNA during the absorption on the graphene oxide. So that is the reason why we keep continuing the simulation until 200 nanoseconds. And we deeply believe that 200 nanosecond is enough for our study.
All right. So, well, another question in the line: is it possible to invent a toolkit for detection, to detect the cancer in the future? Could
Is
you
it
do that?
Okay. Actually,
Like a very cheap toolkit for everyone to test the cancer at home, something
okay.
like that.
We think that at the moment, this kind of kit has been widely used in the commercial market.
All right, it's
And
already available.
no,
Right?
no, but not for this kind of things. But
Oh, all right.
it applies for other is applied for other biomolecule.
Oh, you mean another technique somehow?
No, the same technique that I explained here.
All right.
But they use this technique to detect some biomolecule, and then you have the chip that you can put this chip into some packet, and then it show the electrical conductivity of that system. But in terms of normal and cancer DNA that we explained here, it has never been reported before, and we found that it is a good way and easy way to apply. And I think and I believe that in the near future, this can be applied in the commercial market. And I'm not sure if it is cheap enough for everyone to use in your
All
house. But at least you can use it in the hospital and
All right,
with
okay.
a cheap cost that you can screen your cancer risk.
Yeah. All right. Okay. Well, and one more question. On the model potential, there are many free parameters. How do you get those parameters, and how do you validate them? And are they transferable? Well,
Okay.
very technical question.
Technical. Okay, thanks. For the model and many parameter that we use in our simulation, I think that many guys that are working on molecular dynamic simulation, the first problem about the simulation is the parameter that you use in your simulation. And for example, at the first few years that I worked about gold nanoparticle, so the things or the way that we have done in the first few years is to follow other research that they are working on the material or the particle that they simulate. For example, in the case of gold nanoparticle, there are so many people that are working on gold nanoparticle, and they develop the parameter and the force field parameter, everything in that kind of sense, and they develop those parameter, and we bring those parameter and to apply to another or different application in our system. So basically, optimizing or working on parameter is something that is challenging, but in our research group we follow the force field parameter from other literature.
All right. Okay. So, well, there was a question about simulation time. All right. Then I believe that in your research it must be something to do with computational power. Right? You need like a cluster of the computer to do simulation thing, right? Is that
Yeah.
Pardon? So what I mean, the question is, you in your research, you might need like a huge cluster of the computer to do the simulation, right?
Yeah. In our study, it depends on the system that you are working on.
All right.
In the case of what I present here, it's not that big system, but it still has to be conducted in the big cluster.
All right. Okay.
For other work that is going to be public very soon, we work on the system which contain about 1 million atom. So it has to be simulated for quite a long time, and a big cluster has to be is essential. And one thing that can be that can help a lot is the GPU. Working on GPU can help and reduce the simulation time in quite a large or big system.
All right. Okay. So, well, here come to the very interesting question. So, what do you think about the coming of the quantum computer? Then, is it going to help you in terms of simulation, quantum computer?
I think sure, for sure. We somehow that you have to wait for nearly a month in order to get some results of the big system. So, and I deeply believe that quantum computing can really change or can really help this kind of research a lot. And if you have a very high efficiency like quantum computer, it's going to help the calculation or the study on the interaction in the molecular level, especially in a very, very big system.
All right. Okay. So, well, I think it's about time. Well, then I would like. Well, I think. If the audience, if the online audience have more question, you can put the question on in the comment. All right. I think Dr. Thirapong will have a look later. Right. And definitely less one, I believe, right? So I would like to thank again our speaker, Dr. Thirapong Phongmali, and everyone who stay online with us. Well, I think this more than 1 hour, I believe.
Yeah.
But this is very wonderful talk and very interesting. Okay, before you go, please spend your time a bit on the cell waveform, which actually given in the link will be provided in the Facebook post live and also YouTube live as well. I think please do that, the cell waveform for us, right? Okay, well then see you again in the IF Colloquium number 2 next month. Stay tuned then. Bye. Thank you very much.
Thank you. สวัสดีครับ
สวัสดีครับ Bye.